did I do that wrong?
32.8 is right, I think. 32.1 for the chicken joints. What are you doing? You're adding together?
Yeah.
Okay. And when you do the magnitude of that, you get about 25.
All right.
All right. Cool. Wait, let's write the answer on the board. So, 35.01. Is that it?
Yeah. So you want units?
Radians per second squared, right?
That sounds right.
Bravo. It's good to do it real time like
Yeah.
that. And you do the debugging, and so you get to learn a little more than just copying from what you have already done.
I just put in like brief notes,
Right.
basically
Makes
like the
sense.
rough steps. I didn't write it out comprehensively because I didn't want to just copy off my notes.
That's a great way to learn.
But one of my notes was not to
Legible.
put a power 4 instead of a power 3. So, all right,
Power to
cool.
you. Andrew got a fun problem.
Yeah, let me give you the mic. Give me a sec.
Okay, so here we have two children playing on a park. They're on a seesaw and it's on a merry-go-round that's also spinning, and then that's on the ground. So there's a few different reference terms we have to consider. So first I'm going to begin by defining coordinate system and then some values for the reference frame. Okay, so this is kind of like the ground. I set up this problem in a way that made it easy, but it may initially seem a little bit complicated. So this is like kind of like the coordinate system I'll be using for the ground, but the main coordinate system I want to look at is like the coordinate system for the seesaw. So I'll use these dashed lines to represent that. And then, so this is what this is essentially saying is, if I notate this as the I hat axis, these two coordinate systems of the ground and the seesaw share the same I axis. However, the seesaw is rotated. The seesaw I'm going to represent as B for board, which is what they use in the problem. The seesaw is rotated by an angle theta. And that angle is the same for this J hat and K hat. I guess I should write it more horizontally or vertically. K hat axis. Okay. And then we have these angular velocities, omega h and omega v. So one important note is if we use the right-hand rule, we can see that in this axis, which is the k hat before rotation, the angular velocity is in the positive direction. However, if you look in the I-axis, this is in the negative direction by the right-hand rule, which is, this is what's given in the problem. So we just have to consider that when looking at our givens. So I'll just do some further notation for clarity. So seesaw is represented by B. Ground is represented by G. And then I don't believe I use this in the problem, but MGR, it's the merry-go-round that this seesaw is on. I'm representing this with J, just because that's what's told in the problem. And then the stone, which is going to be in the next problem, will be represented by P. I'm guessing that's for point. And then so our omega V value is 2.2 radians per second. Our omega h value is negative 2.9 radians per second. And our omega v dot is 1.2 radians per second squared. And our omega h dot is 2. Wait.
1.2, 2.1. It's the other way around.
Yes, this is supposed to be 2.1 radians per second, and our omega h dot is actually negative 1.2 radians per second. And so, as I was saying earlier, that negative is coming from this arrow being in the reverse direction from the right-hand rule, which would make it negative. Okay, and then so first, what we want to do is find the angular velocity. Well, okay. You made a comment about it has to be. It can't be. Oh, actually, never mind. That's okay. That's right. So we have the angular velocity of the board with respect to the ground. And that is composed of the angular velocity of the board with respect to the ground. I'm going to use a different notation system just to be a little bit more clear. So with the board with respect to the ground, it's going to be a little cluttered just because there's a lot. So this is from the h component, and this is in the I hat direction as we defined earlier. And then there's this v component of the board with respect to the ground. And now we have to look at the sine, or this multiplied by sine theta. And that's to account for the rotation by the seesaw. And this will be in the j hat direction. And then there's also this component. If you look at, instead of the sine of theta, you look at the cosine of theta. Then there's this component in the k hat direction. And this is all in radians per second.
The first term there, the omega doesn't require a underline.
It does. Oh yes,
Yeah.
because it is just a component of the vector. Okay. And then now we find the derivative of this to get the. Let's see. Well, we're asked to find the magnitude of angular acceleration. So we start by finding the angular velocity, and then we do the derivative to find the angular acceleration. And in order to do this, we have to use the product rule, because this is a function, and then this is the sine theta is a function. So let's see. In order to account for that, we have to do the product rule. So the derivative of this is omega dot for the h component from the board with respect to the ground in the I hat. And then we have the derivative of the first, which is omega dot of the v component with the board with respect to the ground, sine theta, lots of words, plus omega with the board with respect to the ground of the v component, cosine theta, and then times the derivative of theta with respect to time, and that's in the j hat direction. And the change in theta we can represent with or the rate of change of theta we can represent with WH, because you can see they're related as they're both kind of showing the angle of the seesaw. So this is like the angular velocity, and that's the angle changing with the seesaw. So I can write that theta equals 30 degrees because that's what's given in the problem. And then theta dot equals omega h equals 2.9 radians per second. And this is the negative of this sign because, is that correct? This actually also may be negative. I plugged in a positive answer though, and I got, Okay, I'll have to recompute a little bit, but I believe this is positive, and I'll think of how to justify that in a bit. But also, so finding the k component, let's see, we do omega v of the board respect to the ground, and then we do the derivative of that times cosine theta, and then we add that with, I don't need this underline. Product rule, which would make this negative sine theta times theta dot in the k hat direction. And this would all be in radians per second. Okay. And then so if we plug in values, so to find the w dot h component, that's actually given. So we can just plug in, very messy, negative 1.2 in the I hat direction. And then plugging in omega dot for the v component, that's given, it's 2.1. Sine theta is sine of 30 degrees, and then the omega v is given, it's 2.2 radians per second, and then the theta dot, or the derivative of theta as we defined earlier is 2.9. Let's see. I believe this is positive because the angle is increasing positively. I may be mistaken with the exact justification for that. But anyways, if you plug in the values, it'll give you a value of negative 4.475 in the j hat. And negative 5.008 in the k hat. And that was found by plugging in all the above given values into this equation. And then these are all in radians per second. And now if we want to find the magnitude of that, we do the square root of the square of all the components. I can just neglect the negative signs because they're squared. And that comes out to be 6.822 radians per second squared, which is the final answer. And then I have the next problem, which is a continuation of this problem with different values. So I can erase most of this, but I'll leave up the, I'll leave up the reference, or the coordinate system. Okay, I'll just put this here. All right, so in this situation, now we're looking at, well, it's still a seesaw on a merry-go-round on the ground. And now instead we're looking at a stone being slid from one child to the other on the opposite side of the seesaw, and we want to find the magnitude of the velocity of the stone relative to the ground. So we have to do a relation of the velocity of the stone to the board to the merry-go-round, and the merry-go-round to the ground. And once you find all those like velocity relations, well, I guess I shouldn't say velocity relations. I guess the velocity of the stone with respect to each of those coordinate systems, then you can find the velocity with respect to the ground of the stone. And the stone, you can talk about velocities because it's like
Kinematic relations.
yeah, it's pretty much a point. Okay, so I'll start. So our omega v is given as 2.6 radians per second. Let's see, our omega h is given as 2.4 radians per second. And let's see. I guess if we wanted to find the reference, actually no, that's angular velocities. Okay, never mind. And then so the distance between the child and the middle of the board, I believe, is 5 feet. So I'll put d1 equals 5 feet. And then it says that, let's see, the stone is 1.6 feet from the girl. So d2 equals 1.6 feet. And then so if we do d1 minus d2, we can see that I'll define it as d3 equals 3.4 feet. And this value represents that the stone is 3.4 feet away from the fulcrum of the seesaw. And now I'll kind of write out symbolically what I was talking about before. So the velocity of the stone with respect to the ground is the velocity of the stone with respect to the board plus the velocity at that point of the merry-go-round with respect to the board plus the velocity at that point with respect to the of the ground with respect to the merry-go-round. Did I define that correctly? All right, I believe so. And then we also have this relation that I guess I can represent with the underline.
So velocities are always of points, not of bodies. So you need to specify which point of the body.
Okay, so I guess with the stone to the board, that's
So
fine.
stone is pretty good, okay, because you're assuming it to be a particle.
Okay, then with the merry-go-round to the board, I guess that's at the point of where the stone is on the board. And then that point kind of...
So you'd call it P bar or...
you said B bar?
Yeah.
Okay. I guess B...
P bar.
Oh, P bar?
Yeah, because it's the point P at an instant, right?
Okay.
Yeah, so whatever you have written on the as a post superscript, that should be of a particular point on the seesaw.
I see.
Yeah.
So this
that
could
we
be
can call it P bar
P...
with a over bar.
Okay, P bar, and then this would also be P, maybe like double bar. I'm not sure if that's a notation being used, but we'll go with it for now. Okay, and then a relation we can use is that velocity of a point is equal to. This is for 2 points with respect to each other on a body. So
Fixed.
Sorry. Oh yeah, 2 fixed points on a body, and So you can find this by crossing the angular velocity with the r vector between the 2 points. And then so the velocity of the point or the stone with respect to the board is negative 3.8 in the j hat direction feet per second, and that is just a given in the problem. It says the velocity relative to the board is negative 3.8 in the j hat direction. And then now we find the velocity let's see, of the point of the stone on the merry-go-round with respect to the board. And then so you get that that's equal to, let's see. Oh, we also have to consider that the same thing as before, this is negative because in the positive system, well, in our positive system, this is negative. So this, even though it's being represented as a positive number, since we want this negative, or this rotation to be positive with the right-hand rule, I'm going to write this as negative. It's not really coming out correctly. Okay. And then so we have. So right now I'm ignoring this VP term because I'm going to add them all together afterwards. So this addition or change in, I guess, difference in velocity, sorry, would be omega h, which is negative 2.4. And then this is in the I hat direction, radians per second. And you cross the distance that the stone travels. So that's 3.4 feet. And that's in the j hat direction because that's how we defined the coordinates, the axis of the stone traveling with relation to the seesaw. And that's in the j hat direction, feet. And this comes out to be 8.16. And then you do I cross j, and then you get the k hat direction in feet per second. And now we find the velocity with respect to the merry-go-round of the p double bar. And we get, let's see. So we use this omega v since that's how the merry-go-round is rotating. It's 2.6 radians per second. And this time it's in the k hat direction. Oh, so this time this is a different problem. So so now I'm using the unit vectors of the ground. Oh, the I hat remains the same, but the ground as our main coordinate system. Okay, I forgot to make that correction. And then so that'd be in radians per second. And then we cross it with the same position vector of 3.4 j hat direction, feet. I guess the j hat would remain the same. Is that necessarily valid? Because these aren't. I guess we can write this as j hat, and then this is j hat prime. So then, okay, yeah, because we still want this to be j hat. So, and that equals negative 8.84, and then you cross k by j, and that gives you the negative I hat direction. And then so we sum all of these components, and you get that the velocity of the stone with respect to the ground is equal to the I hat component, which is negative 8.84, and then the J hat component, which is negative 3.8, and then the K hat component, which is 8.16 feet per second. And then now we want to find the magnitude of that. So we do the square root of 8.84 squared. Again, neglecting the negative signs because it's squared, so it doesn't really matter. And then plus 8.16 squared equals 12.61 feet per second.
Final
And that's the answer.
Sorry to be picky, but this is kind of redundant, right? Either you put a J hat or you put it in this form.
Oh, yes. That's okay. That makes sense. Cool. Oh, yeah.
So mine's a little suspiciously easy. So we're given omega spacecraft with respect to Earth. It's 1.71 B1. Radian per second. These have little hats. And then we're also given omega top to spacecraft. I guess the problem, I didn't really explain it. There's a top spinning on a spacecraft that's rotating Earth. Okay, and then basically we know that the top in respect to Earth, omega top respect to Earth would be omega top respect to spaceship plus omega spaceship respect to Earth. And then you just add those two vectors together and you're going to get that omega top to Earth is equal to which then it asks for the magnitude of that, and then when you take the magnitude you get 7.4972, which is the answer. Here's my suspiciously easy problem.
That's stitching the nose this way rather than that, which is what you did.
Alright, so where do I work here? So we have to find the magnitude of the angular velocity of the spinning on reference frame of the Earth. So it's kind of a problem, but like, yeah, we can. It's doable. Here, yeah. So this equation here. So one thing that I'll just make you give it to your attention. B1, B2, B3 are just like I, J, and K. So I will use them that way. So this would be alpha top by Earth is equal to alpha spacecraft by Earth plus alpha top by spacecraft plus alpha spacecraft plus omega spacecraft by Earth times omega top by spacecraft, B by C. So this is what we have as our initial equation. So this would be 0 plus this would be, this is given, yes, where is it? 0.0, why can I not see it? Okay, yeah. So this would be, hold on. Do I have the wrong problem? Oh, okay. Yeah. Shoot. I did not see that. Hold on. Yeah, I've to reference Earth. Sorry, I did not see it. Shit.
Is it the same problem in 2 parts, or is it just
No. Sorry, my bad. It's the same thing. I have to find in reference to Earth. I did not see the number there. Sorry, my bad. Pretty easy problem though. Yeah. Just notice this. Yeah. So we are given alpha of t as well. So like, yeah, we will use alpha of t here, which is 0.06 I hat plus 0.11 j plus 0.26 k radians per second squared. And the last part, which would be kind of like a matrix, so 1 plus 0.82 j plus 0.35 k as given. And this would be the other one, which is omega of t, which is 8.3 I hat plus 0.12 j hat plus 0.17 k hat radians per second squared. So this would give us 0.0974 I hat plus 2.718 j hat minus of 6.674 k hat. Same radians per second squared. I'll just use another one. So now what we have to do is pretty much multiply alpha. So this would be alpha t or top, which we have to then multiply by omega, and omega of s is given that we just founded times omega top. So this would come out to be alpha of Earth which would come out to be 0.06, 0.11, and 0.26, and this will be plus.
This side, Prashant. Come this side. Get it.
Plus 0.0.
It's common sense.
2.718 and minus 6.674. So this would give us our final answer for alpha top of Earth would be 0.1574, 2.828 minus 6.414. This is what we would get. And then for finding if we have to do modulus of Earth, or not, let's remove this. So here modulus of Earth would be 42 square root of all these answers squared. So 0.1574 squared plus 2.828 squared plus minus 6.414 squared. So this would end up to be root of 49.15, which would give us 7.01 radians per second squared. Done. Sorry, I did not notice that. I did not. Because I had a similar problem. So. I thought this was going to be a longer problem, but it turned out to be quite easy.
I can go through if you don't want to.
I can go through it. Next to, I don't know if anybody's 9 feet. No, sorry.
This is me, but I think it's a great.
Yeah, it's you.
I can still go through it.
It'll be a team activity.
This one is pretty easy. So we derived in class definitions for what roll, pitch, and yaw, depending on the angles and the change in angles. And so pretty much in this case, we're actually given all the values that we needed, and we're asked to solve for, I believe, pitch angular velocity. And so I labeled each component, each measure number, and its component. And so if we're looking for just pitch angular velocity, we know we can just use this equation right here. And so plugging into this equation will pretty much just give us this answer that we're looking for. So let's see. So we're saying pitch angular velocity, which we'll call Q. I'll put the angle on top. And then we equal to this cosine of theta sine of phi plus theta dot cosine of phi. So let's look through the question and see what we're given. So we're told that the aircraft has the following angular rates. Our roll, phi dot is 0, which is not even in this equation, so we can ignore that. Pitch, theta dot is also 0 radians. And so this being 0 radians means that this entire term is 0. So we're just left with the first term now. We're told that the yaw is about 14 degrees radians, so we have our 0.14 radians per second. And then cosine of theta, are we given theta? Let's see. Bank angle of phi equals 22 and pitch angle of 2 degrees. So that means our cosine will be of 2 degrees. And our sine will be of phi, which is 22 degrees. And this should give us our Q in terms of radians per second. Let's plug this in. This is in degrees too, so that's probably important. 0.4 cosine 2 sine of 22. So you get about 0.0524. We can make sure if that's right. Yeah, that's right. That's how you get that.
Alright, then I must have done the next two, which I think one of them might be 8. So So if you want to break it,
That's okay. I haven't done anything for a while, so I'll be allowed.
Okay. So for the next one, very similar to what Nefez just did. Okay. So our equation we're in reference to the Earth. We are looking for the velocity r, and this is given by this cosine theta, and then cosine phi, and then minus theta dot sine phi. So then from here, this is 0. So then this whole term goes to 0. And so we are left with negative 0.17 radians per second. And this is our theta dot. And then we have sine phi, which our phi is 12. So this is 12. And then when we plug this into our calculator, we get negative 0.0353, and this is in radians per second.
Okay, so next we're going to look at similar problem, but this time we're considering the angular acceleration of the aircraft in radians per second. So my approach to this problem was to first define the expression for the angular velocity and then take the time derivative because we know that's how they're related. So just to simplify things, I took a look at the angular acceleration, which is a vector in the aircraft fixed frame, and so we can use our expression for based on the pitch, roll, and yaw.
The angular velocity of the aircraft with respect to the ground.
Okay, so this is the.
So A would be on the right hand side and Earth or I.
So I would say like A with respect to Earth. Okay. And then we know our definitions of P. And we know as well, hold on, that we want to write these as a function of time. And so while we're given that the angular rates of the aircraft are constant, the actual angles of the pitch, yaw, and roll are changing with time because the rates are non-zero. And so that means that we do have an acceleration, and that our P, Q, and R are functions of time. Specifically, I think, yeah, specifically the angles are functions of time. So I'm going to rewrite this with what's a function of time and what's not a function of time. And then an important simplification that we can make at this point is that our yaw rate psi dot is always 0 radians per second. That's a constant. So that means that for the purposes of our angular velocity and acceleration, these terms, which are all multiplied by psi dot, will end up being 0. So to simplify our process, we can remove those now. When we take the time derivative, we're going to take the time derivative of the, if I'm writing the time derivative, is it redundant to put the reference frame here if I have the dot?
No, it is not redundant because what you have written A/E is just the definition of omega itself.
Okay.
But then the derivative can be in any frame.
Okay. So we're going to have our expression and then that means that in order to find the magnitude of the angular acceleration, because these are all unit vectors, we only care about the rates of P, Q, and R. So even if the unit vectors are changing their direction, it's not going to change the magnitude. So then we're going to take the time derivative of our each of our P, Q, and R here. So the time derivative of P respect to the Earth's reference frame as a function of t is equal to theta double dot. And we see here that since the phi dot is a constant with respect to time, that our phi double dot is going to be 0. We look at our q dot term, we look to see what is varying as a function of time, and we see that in this cosine term, there is phi as a function of time, so we're going to need to take the constant theta dot out front, and then we're going to take a derivative with the chain rule. We're going to find that our theta dot will be multiplied by negative sine phi of t multiplied by phi dot, phi dot. And then our r dot of t in the Earth, respect to the Earth reference frame, is going to come out very similar, but this time it's going to be a cosine term. And then if we evaluate these quantities at the incident time, we don't know exactly what the time is, but let's just say at time t naught, then we know all of these quantities. So we know that this is 0. We know our theta dot is given as 0.13 radians per second. And then we have the angle at this given time is 18 degrees. And then our phi dot is 0.15 radians per second. We can do much the same for our R. And then when we calculate what each of these components are, I don't have the values offhand.
we get that this term is equal to .006, and that this term is equal to 0.019, and then when we find the magnitude, and we take the square root, we get an answer of 0.0195 radians per second squared, because both of these terms have radians on the top and then second squared on the bottom, and then one of our radians ends up being unitless, and that's the right answer.
Just a few notes.
Yes.
So whenever you take the time derivative of angular velocity in particular, doesn't matter whether you take it in A or E.
Okay.
So this could be either E or A, but actually you have taken in A because you have written A1 hats over here.
Okay.
Only then you can take those as constants, and you are only left with P dots, Q dots, and R dots. But if you're taking it with respect to E, then
Okay.
it's not so. And PQR by definition are
Okay.
always in the aircraft fixed frame. Okay, you see my point, right? So,
Yes, I do
yeah,
understand.
yeah.
Because otherwise, then you would have three other terms.
Right. So it's not necessary to put E over here. It's
Okay.
understood because
Okay.
PQR are of the aircraft with respect to the ground, but expressed in the aircraft fixed frame.
Okay, and the
So,
reason why we can
yeah.
take it with respect to the aircraft fixed reference frame is because it doesn't matter for the purposes
Yeah,
of angular acceleration. It
just
doesn't
for
matter.
the angular velocity.
Ah,
In fact,
okay.
we proved in class
Right.
that it doesn't matter whether you take it with respect to A or E, you get the same result.
Okay.
But it's not true for any other vector.
Okay. Go ahead, this question.
Okay. Alright, so this problem is kind of complicated. It requires a lot of reference.
Hope it's stable
frame.
enough. The laptop.
This?
You want to put? Is the laptop stable enough?
Mine? Oh,
Yeah,
mine's
yeah.
fine. Yeah.
You can see if you can push it in further.
Yeah. Yeah, I don't think I can. It'll be fine.
Yes.
Okay, so this problem does require quite a few reference frame transformations. So me and Vithi both worked on this problem. Alright. Let's see. Sorry, I'm trying to find my work. Okay. So we're given that a vector from the aircraft center of mass to a point on the wing is along the y direction of an aircraft body reference frame without the magnitude. Okay. So I'm going to first draw out this problem. So we have like an aircraft. That's not the best drawing in the world. So this
Z
is
will be downwards.
Oh, yeah. Oh wait, so this is Z?
That's correct. That's correct.
Okay. I'll take that negative. Okay. So I think right now we are in the inertial frame of reference and we're trying to convert to the earth frame of reference. Is that correct? So first I wrote down what they gave, which is they give us the Euler angles. So phi is 13 degrees, theta is 17, and is that psi? Psi is
Yeah.
118. It's the orientation of the aircraft relative to the inertial reference frame. So I'm just going to put I there. And we're also given that vector d in the inertial reference frame. So we're taking the center of mass as the origin of the inertial reference frame, and that is 0, 6.30 meters, that's only in the y direction. So now what we first have to do is transform from the inertial or the body reference frame to the earth reference frame. So there is a series of matrices that I used for that. It is, okay, so it's the rotation matrix R, because the inertial reference frame is transforming to the earth via angles, not necessarily by distance, because we aren't given that. So what the formula is so I have to zoom in. So that should be R, Z, psi, plus, or times, or cross R, Y, theta, cross R is phi. And now for each of these matrices, so we're given the angles. So I'm going to denote, well, we can number these 1, 2, and 3 for the sake of simplicity. And because this is on the z-axis, we're going to take everything relative to the angle psi. And on the z-axis, the z component will be 1. So the matrix here will be cosine psi minus sine psi 0, which is the x rotational vector, and then sine psi right, and then here 2 is relative to the Earth body frame will be 0, 1, 0. That's y hat in the middle. And then the rest is relative to theta. So cosine theta, 0, sine theta. And on the bottom is negative sine theta, cosine theta. And then lastly for r, sorry, that's my bad. I meant to say Rx here. So we take the unit vector for x. And this should so these are the transformation matrices with regards to each of the angles given. And I should have done this first, but we have to convert the degrees to radians to make our lives easier. So that's 0.227 radians approximately. That is 0.297, then 2.06. Alright. Yeah. So now we can use these radian angles to compute the actual values of each rotation matrix, and then we can do the cross products here to figure out the final answer, and we're just going to take the z component of that final answer. So this is all just a lot of number grinding. Do you want me to write out every single thing?
No.
Okay. So if we plug in psi into here, we should get, okay, we get negative 0.515, negative 0.86, I'm just going to do 3 sixths just to be consistent with myself. And then so basically what we found so far is the exact rotational transformations on each axis from the initial reference frame or the body reference frame to the Earth reference frame. So finally what we have to do is combine these 3 rotation matrices into one rotation matrix. And how we can do that is first crossing these 2 and then crossing this with that. So that should
It's not cross product, it's just a matrix
Well, just-
multiplication.
Yeah, just the multiplication, yeah. I don't know. I mean, I guess it doesn't matter either way.
There's no symbol there.
Yeah. I guess I'll put parentheses. Okay. So I should erase. I'm just gonna put X there, doesn't matter. 0.956.
That's okay. You can just write the final result when you multiply those three matrices.
Okay. So basically, if we take those three matrices that we found and multiply them all together, the final result should be 0.493. So now, finally, we can transform the initial velocity vector using R because we know that V in the Earth reference frame equals R times, no, sorry. Oh yeah, it is R times V. Okay, R times V in the inertial reference frame. So we can just do this times 0.630 meters. And that should get us a final answer of negative 5.25, 5.26. So, yeah, so this is the final vector in the Earth reference frame. And they did just ask for the Z component, so that would just be this guy right here. So basically or it's not a vector, is it? No, it isn't. Is 1.36 meters.
Yeah, that's not a vector, it's just a measure number, right?
Oh, yeah,
Yeah.
okay. Yep. Yeah, so the main concept of this problem is relatively simple, and starting off with the body reference frame was probably beneficial in terms of making it easier to calculate the initial angles. So let's just say in a real life scenario, if you have like a stunt plane, for example, and it's going at a certain speed and it's rotating in the air, it would be really difficult to calculate its pitch and yaw angle relative to the Earth. But if you're like a cameraman and you're going in a jet beside that jet, it would be way easier to calculate that in the inertial reference frame and then transform it to the Earth reference frame. I mean, can't think of like a particular application. I guess it would be to like, I don't know, if it is a stunt plane, if it's doing a certain show, has to do a certain loop, then you would need to know its angles relative to the Earth. So I guess that would be one practical application.